the menu for today, which is becoming more and more sloppy in a sense. We're not going to calculate stuff anymore. We're just going to say, let me just approximate things and see whether I can kind of get away with not doing very much work at all. And that's the idea behind the multipole expansion, which again, I think is something you've studied in the past in a kind of restricted form, but we'll try to be, a bit general about this here. Okay, so let's see how this goes. Now, the point of the expressions we have for the potential, is that we always have a spatial dependence form that looks like a combination of factors 1 over r minus some r and let me call it r source. Okay, so if I have a little source somewhere, this is our source. It's got a charge here. Then I know the potential is just 1 over 4 pi epsilon 0. Charge of that thing divided by the distance that I have here. Okay, so we're just going to try to maybe simplify that expression here in a certain form. So the starting point we're going to have is to say that we're very far away. So say that R is much, much bigger than this RS. Said otherwise, I choose a certain origin here, and my observation point is very far away. So here there's, good distance, and here's my observation point. And I'm just writing it like that to simplify things at first. So I've got my origin. That's where I put my 0 coordinates. My source is sitting here, but my observation point is like very far out. And it's very tempting to look at this thing here and try to do some Taylor series for this dependence here, right? So this is what we're going to do. So say that we've placed the things in this direction here. So let that be the z-axis. Okay. So for this particular situation here, if I have 1 over r minus r source, then really let me write this as 1 over r minus r source, if you know what I mean. So this is the vector position, but then the distance here, this is rs. And then, of course, the little scalar r here is just this distance here, linking the origin to the observation point. The point is that I can write this as a Taylor series. It's just a geometric series. So what is it? It's just 1 over r times, well, what do I have? 1 minus rs over r to the power minus 1. Okay? And provided rs is closer to the origin than r, this number is less than 1. Therefore, there is a convergent series for this, which is just 1 over r. And then I do a summation from L is equal to 0. It's just the geometric series, rs over r to the power L. Okay? So that's completely legitimate. The only condition is that my observation point r is further away from my origin than the source point. And essentially, that's it. Right? So this is the basis for the so-called multipole expansion, and we'll see how that works. Okay, so that's what we have in this case. Everybody's happy with this? Yeah? Question? Oh, sorry. Summation L from 0 to infinity. L is an integer going from 0 to infinity. Okay? So that's the statement we have. All right. So now we're going to do a little trick, which you'll hopefully like. So say the geometry say we've got a different geometry. We've got the origin and we've got the RS. And maybe I'll even put it somewhere else. Okay, I've got the RS here. That's my origin. And say I put the R then here. Okay, so it's not the same lineup that we have. Here they were co-aligned, and I could transform immediately this thing into a function of scalar distances here and there. But now I've got a different arrangement because the vector RS is not aligned with the vector R. So what do we have here? Well, we've got a more complicated situation, and we'd like to write immediately what the answer is. So we can actually do this because what do we have in this problem here? We have an axis, which is the axis going through the origin and R. And around this axis, the potential is going to be azimuthally symmetric. Okay? Because I'm not changing the potential if I rotate the whole system around this axis. And we already know what the general solution of the Laplace equation is in the case of an azimuthally symmetric configuration. Okay? So why do we know that? Maybe just to remind you what this was, I'll go back to this here. So we had these notes here, but then the important statement we made, which was the one that I wanted you to kind of be able to use, derive once in your life, but then use. The statement that we have here made last time is that the solution to the Laplace equation in the presence of azimuthal symmetry has to take this form here on the board. Okay? The only thing that we have not determined, of course, are the coefficients AL and BL. Okay, but the general form for the solution is going to look like this. Question.
Azimuthal means cylindrical.
Azimuthal, you can think of cylindrical. It's not so I kind of don't really use symmetrical because it can look like, you know, a flower pot, which is not a cylinder, but it has one axis of rotation, which leaves it invariant. So yes, for problems with azimuthal symmetry, you could choose to use cylindrical coordinates, but you don't have to.
And why in the example that you just showed before, why is that situation asymmetrical?
So this situation here, R is my evaluation point for the potential. And I'm going to want to evaluate the potential everywhere in space. However, I've got my origin, and I've got the axis leading me to the source charge here. And if I was to take this axis and just rotate around it, the value that I would measure for the potential would be unchanged, because my distance to the point does not change under the rotation. Okay?
Yeah.
Right? So what I'm doing here is that I am turning around this axis here. And essentially I'm computing the value of the potential all the way on these great big circles in here. But on all these circles around this axis, I'm getting the same answer because the distance is the same. Are we cool? So that is what azimuthal symmetry means. Here we have a single source charge, but we're just doing it like that. Okay? So that's the statement here. So here we have an azimuthal symmetry. And the solution must be of the form that we had seen before. So that means if I was to now just use the spherical coordinates around this axis, I would get a potential that does not depend on the phi angle because it's azimuthally symmetric. It depends only on the distance and on the polar angle. Okay, so what do I have? It must be of the form that this phi of now the distance that I have between these. So here I would have you know, the certain distance here, and then a certain polar angle here that I would now, yeah, so that would now be my theta, and that would now be my r. Okay, so phi of r theta has to be summation L is equal to 0 to infinity of a L r to the L plus BL divided by r to the L plus 1 times the Legendre polynomial PL of cos theta. It has to be like that. Okay? Sorry, I mean, don't you love my handwriting by now? AL r to the L plus BL divided by r to the L plus 1. Okay? Maybe I should teach electrodynamics just orally like this and never write things down, just do like in the old tradition of Homer and things, just recite things. Yeah, sum L to Z from 0 to infinity, AL r to the L plus BL divided by r to the L plus 1, close parentheses, PL of cos theta, blah, 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 and then accompanied by guitar and whatnot. You'd remember this. Okay? Question?
Maybe I misunderstood the distance from items and why it is not strictly symmetric.
Okay, so the question is, why is this not spherically symmetric? I have put my origin here, and I have my source charge at the, you know, from the origin at the tip of this thing here. If I had spherical symmetry, I could choose any rotation axis and rotate any angle I want on that axis. So here, if I choose my axis along here, it's cool because this doesn't change. My position of the charge doesn't change. Source doesn't change position. However, if I choose this axis, then I rotate and the position of the charge changes. So this is not rotation. The configuration of the source charges is not rotationally invariant according to an arbitrary axis. Full spherical symmetry would require invariance of the distribution of charges under rotation under any axis.
But there's also directions, right?
So no, origin is really just the place at which we put our origin of the coordinate system. It's a pure mathematical abstraction. It's got no physics to it whatsoever. I could. Okay, so in a sense, it's a very good question. We are making a choice of an origin on here. And the particular coefficients of the expansion that we get for the function depend on this choice of origin. But the function does not depend on the choice of origin. Okay? So said otherwise, take a one-dimensional function f of x. If your Taylor series converges, you can expand f of x around a point x0, or a point x1, or a point x2, or another point. And provided a certain patch is within the radius of convergence of these Taylor series, all the Taylor series equate the function in that patch. But all the different series, the one expanding from here, or the one expanding from here, or the one expanding from here, they are different series. They take the same value, but they are different series. So it's the same thing here. The function phi is independent of the positioning of the origin, but the expansion that we write for it depends on the position of the origin of your coordinate system. Okay, and there are deeper theorems later that we can come to, but for now, I'll just say it like this. Yeah, do you have a question?
Yeah, can you just quickly outline
So the in the last lecture, I essentially bullied you mercilessly because I had pre-written the spherical coordinate separation of variable storyline. Okay, so I just threw this at you. Now it's me throwing the kitchen sink at you. Okay, and the idea was that when you look at the separation of variables for spherical coordinates, you end up separating not in x and y and z, but in r, theta, and phi. And all the phi dependence I'm actually not even mentioning here, because that leads to these YLM polynomials, which you might have seen in quantum mechanics if you've done atomic orbitals and things. That also fits here, but we leave these out for simplicity. So here we have separation of variables in the radial coordinate and in the polar angle coordinate. And the equation for the polar angle itself has as solutions these so-called Legendre polynomials, which, you know, I didn't spend much time on this, but you know, as far as you're concerned, you know, they exist and you've got the tabulated form for them. They are the polynomials which are essentially, you know, finite degree polynomials under a flat measure in the interval -1 to 1. Just that is enough to define them up to it. Okay, so for that thing, the details come from the particular separation of variables in the spherical coordinates, looking at the differential equation that you get for the angular bit, and noticing that you can solve it with these polynomials. Okay, so it's not really answering your question, it's telling you where to find the answer. Okay, but at that point, it is constructive, because once you've assumed separation of variables, the differential equations that you get for the radial and the angular part, they're non-negotiable. That's what they are. And you can find a basis, a complete set of orthogonal functions to solve these equations. And in the angular case, it's the Legendre polynomials. You could actually choose a different set of orthogonal polynomials here, and you would get a legitimate solution as well. It would just not be quite as pretty, but it would still work. You could say, no, I always do my sine functions and things like that. I don't want to do anything else in life but having my sine. And then, fine, you can do it, and then you just realize that you always get these polynomials of, indeed, cosine of your angle. You say, okay, at some point, you know, let me just write cosine of theta as some other variable. Then it's just these polynomials that come up. Okay, so that's the logic here. Yeah, not a very satisfying answer, but you know, it's like learning how to use a hammer, yeah, or maybe a more elaborate like Japanese saw, you know, to do things. Okay, that's what this is. Other question?
Sure. Maybe it's a good idea if after the first homework experiment, maybe the second question.
Yeah.
Maybe it could be revision in the tutorial.
Yeah, we're going to. Yeah, absolutely. Yeah, because there was this fun potential problem where you needed to do that, and then essentially you could exploit these spherical coordinates to help you here. So yeah, I mean, I think this is going to be discussed again. Make sure. Okay. So so that's the idea here. Now, okay. So what I'm saying is that in this particular situation, it has to be that the solution has this general form here that we have given. Okay. The question is, what are the coefficients AL and BL? Okay. So how do we compute the AL and the BL? Well, we say, okay, let's consider a simple situation where I put back my evaluation point R on the axis. Okay. So if I put back my evaluation point R on the axis, that means I'm just putting the angle theta to 0. Okay? And when I put the angle theta to 0, so if I do this, right? So put R back on axis theta is equal to 0, then I have that phi of R, theta is equal to 0, is, I'm just using this expression, sum L0 to infinity, AL R to the L plus BL over R to the L plus 1. But now I have cos theta is 1, and I stated in passing that every single Legendre polynomial evaluated at an argument of 1 was equal to 1, just by definition of the scale. All these things fall out. So that's my expression. But this has to equal that thing here. Okay? Because that's the one that we got from straight Taylor series when I'm on the axis. So there you have it. So all the coefficients are just immediately known. So all the AL are 0, and the BL, you see what's the BL? I have 1 over R to the L plus 1. So BL is just equal to RS to the power L. And I'm done. Question? Because, so the question is, why can I put back my R on the axis? Because the general form that I have here is valid for all R and for all theta. And therefore, I can restrict it however I want. And I can evaluate that expression at theta is equal to 0. The expression still holds. Therefore, I can use that, if it happens to be convenient, to read off some coefficients, because the coefficients do not depend on R and theta. And therefore, by choosing this, theta is equal to 0, I obtain a simpler expression from which I can manifestly read off the coefficients, because I've had a different way of calculating it in that particular circumstance. Okay? So now you see the kind of power of the reasoning that we're making. We're kind of writing down the general solution. We're saying, we know this solution in one particular case here, and just that little thing is enough to give you all the coefficients of the general solution. So then you say, fine, bring it on, give me whatever R and theta you want, and the solution is that one. So what's the general solution? The general solution is simply that phi of R and theta, now for any theta, right, is just the summation. L is 0 to infinity of Rs to the power L, which is my BL, divided by R to the L plus 1, PL of cos theta. And that's it, I'm done. Okay? I didn't come up with it, but that's the idea. So do you understand the reasoning? You see, in a sense, that's why mathematics at some point becomes very powerful, because it lifts you from solving individual particular circumstances to providing completely general things. In a sense, you become even uninterested in what you need to fit, because you know that this particular machine that you can throw at it will grip and fit and do its job. Okay? And that's the general questions at the back there. Okay, so where do the A and B come from? So last time, again, we did in detail the separation of variables for Cartesian coordinates. So let me start my answer back there. What did we do? In the Cartesian case, we had these orthogonal functions solving our differential equations. And then we had these coefficients, you know, C, D, that we discussed in detail and whatnot. So these are the, if you want, amplitudes of the basis orthogonal functions appearing in the linear combination of the great big summation that represents your potential. So the A and B coefficients, now same story, different details. The A and B coefficients are for separation in variables in spherical coordinates. They are the coefficients of the two mutually independent radial solutions to the radial part of your equation. There's one that is regular at 0, blows up at infinity, and there's one that is regular at infinity but blows up at 0. So these are the A's and the B's. Okay, so here, kind of writing it for a particular L, but you can choose any L in here depending on what the index of the equation is. Okay, so they're like the expansions of these linearly independent solutions to your radial equation. Yeah? You had a question also? Just,
Yeah, never mind.
is it okay? Or, yeah? Okay, another question. Yes. So yeah, indeed. So good question. Good to emphasize. Here we started from the assumption that our observation point was further away from our origin of coordinates than the source. And yes, everything we are writing here is contingent on having a convergent expansion. And the expansion will be convergent if the observation point is further away. You could actually write a different expansion where all your charges are further away from the origin than your observation point. Then you would expand the other way. You would expand with powers of R over Rs. And then you would get non-zero A coefficients, but zero B coefficients. That would still work. But in this particular case here, we choose to put ourselves away. But it's just to develop machinery that will be applicable in those circumstances. Yeah? Okay? Yeah, so that's the idea here. Okay, so since cos theta can be written as, okay, so here r hat dot r source. Okay, what am I doing here? I'm just using a little notational trick. The cosine of the angle here, if I have a unit vector in the direction of the source, unit vector in the direction of r, cos theta is just the scalar product between these two. So I can kind of lift the representation completely from any particular choice of axis here. Okay, so what we can write in general is that the potential, let me write it like this. So the potential now at a given position r is going to be 1 over 4 pi epsilon 0. The summation L is equal to 0 to infinity. And let's see, am I maybe I'm going a bit fast, but I'll do it anyway because I'll explain it to you. You see, 1 over r the L plus 1. Okay, and now I'm going to lift up my thing. So we've done it for a point charge here, but I can have by superposition a whole collection of these objects here, each of which living at its own position here. So in that case, what I would just get are different values of this this RS here, and with these different angles and whatnot. So what I would have is an integral over a certain volume that's occupied. Maybe what I mean is this, right? So I have my origin here. I have a blob blob here with rho charge at a certain RS, where RS is now living inside this blob, which is full of charges. And I've got my observation point here, further away from the origin than any charge within this distribution here. So that's my volume V. So I integrate over this whole volume of source charges, E tau source. And now, well, what do I have? I just have the actual position of the source itself to the power L. I have the Legendre polynomial of the cosine of the angle with that particular source, which is just this R hat dotted into that particular RS hat. Okay. And by linearity, I'm just doing it for the density of charge at that point RS. Okay, and this is in the notes, I call this equation P Legendre, so potential as a Legendre sum. Okay, so and this holds if R is greater than RS for all RS. Okay, so once again, if my observation point is further away from the origin than any charge inside this this volume here. Okay, so this is the kind of important equation that you have here, and I guess we'll take a little break now, but then we'll just explicit a bit more how to use this this object here. Okay.